So, we would like to find the area of an ellipse. Using Green's theorem. And I think I gave you a tool, right? I gave you a parameterization.
Yep. Yeah.
Yeah? So x of t was a cos t,
Yeah.
and y of t was
B sine t.
b sine t.
So you just gave us a formula, but we have to use the parameter.
Oh yeah, and then there's a formula for an ellipse, right? Which is x squared over a squared plus y squared over b squared is 1. Okay, and then in my head I also have a picture of an ellipse. Yes? Okay, which is like a in this wide and b in that wide. And minus a and minus b in those wide. Yes? Okay, so thoughts. What do you start with to find the area of something?
An area?
Yeah, you do an area integral, right? So you take the integral over your shape. So integral over ellipse of 1d area. Okay? Yes?
You had a video tutorial on your YouTube channel where you demonstrated Green's theorem, and it was this exact problem, but you started with x dy instead of 1d area. Or does that turn into x dy?
It's because
Yeah, so this is an area integral, right?
Yeah.
I would like to turn this into a line integral using Green's theorem.
Yeah.
And so the very first thing I should do is conjure a vector field, right? Where this guy here, this 1d area, right? I'm thinking about this as the partial with respect to y of q, or with respect to what of q?
oh, dx.
X, right? Partial q x, partial p y. So I'm thinking about one is that. What are q and p?
Components of the vector field.
Yeah, they're the components of the vector field, right? So I want to get 1 out of this thing. What's the easiest way to get 1 out of this thing? Put in
1 for q.
1 for q, right? Well, 1 for the q part. So to get 1 out of the partial of q with respect to x, you need to make q equal to x. And what did you make p equal to? 0, right? Is this the only way to do this?
No, that's an easy way.
No, of course not. It's just an easy way. You guys see that? So this is where I'm applying Green's. I'm saying, okay, by Green's theorem, right, that's this arrow, I can turn this into the closed integral around the curve of x dy minus 0 dx, right? You guys cool with that? Okay, but now I've traded. So I've traded pain in the ass area integral for probably pain in the ass circle integral, right? Line integral. So I think I need to get a C that's going to work with Green's, right? So what do you need about your C in Green's theorem? About your curve. You need it to be piecewise smooth, counterclockwise oriented. So I'm looking at this thing, right? And I'm thinking, okay, it's definitely piecewise smooth, right? Okay, then I need it to be counterclockwise oriented.
You can set that up in limits parameter.
So if I do cosine and sine, right? That's like my usual circle parameterization. Does that go counterclockwise?
Yes.
Yes. So I'm checking. Piecewise smooth. Check. Counterclockwise oriented. Check. What else does it have to be?
Simple.
It has to be simple.
Closed.
Okay, is that simple?
Yeah.
Why?
It doesn't cross.
Yeah, it doesn't cross itself. Cool. Simple and closed.
Yep, it reconnects with itself.
Yep, it reconnects as long as I go all the way around. So I have to be careful to make sure I go all the way around. And then I also need it to bound the area I was talking about. So I'm just checking, is the curve that I'm talking about, is that the boundary of the ellipse?
Mhm.
Yeah. You could screw yourself up if you messed up the parameterization, right? Like if you did x of t is cosine and y of t is sine, yes, that's a piecewise smooth, clockwise, simple, closed curve, but it doesn't bound the thing you started with, right? So like, yeah, it's the area, it's going to be the area of something, but it's going to be the area of something else. You guys all see that? Okay, so now that I got this, and I have my parameterization, what do I put in there? Yeah, put your stuff in there, right?
Yeah.
Okay, so this is going to be the integral from 0 to 2 pi. That's getting all the way around, right? And then what's x?
A cosine t.
Okay, a cosine t. And then you need d.
Y.
So what's y?
B of sine t.
Well,
b sine t. I probably didn't show you guys this cheater trick that you can do. What's d of b sine t?
D cosine t.
Yeah, B cosine t.
So you get the integral from 0 to 2 pi of a cos t, b cosine t, d t. Where did the t come from?
Well, now you're integrating with
Y
t.
of the
Y.
part, the derivative
Yeah,
of
your
y
d of
t.
y, because
Yep,
it has
there,
to be
yep.
in respect to t.
Chain rule, right?
Yeah.
You guys cool with that? Okay, so I got this, which is
A B
a
cosine.
b, the integral from 0 to 2 pi of cosine squared t
dt.
dt. Okay, then what?
That's my identity for 1/2 1 plus cosine t.
So hit this with a half angle, right? So you get AB over 2 times the integral from 0 to 2 pi of 1 plus
Cosine of 2t.
cosine 2t dt. Right?
Yeah.
And then from 0 to 2 pi, or wait, which part's easy?
Great.
Cosine 2t, because that's 0.
Yeah, cosine 2t is an integral of a trig function over how many periods? 2. You guys got that? Cosine of t going from 0 to 2 pi would be 1 period. This is cosine of sped up t,
But
right?
the important part is
So we're going 2 periods, but the important part is that it's 0 anyway.
yeah, it's over the exact amount of periods. So
And so you get out of this, so we get out of this
A B pi.
AB
Pi AB.
times pi. Oh, yeah, and then we should check this against our intuition about circles, right? So I have this thing where I'm pretty sure the area of a circle is pi r squared. So when is a circle an ellipse? No, wait. When is an ellipse a circle?
When A equals B.
When A and B are both the radius, right?
Yep. So when
So would I get r squared, pi r squared out of that
yep.
if I put in r and r?
Yep.
Yeah, that's cool. Cool, neat. This was actually pretty chill, right? Anybody try to parameterize the area integral?
I did
Oh,
something
God.
stupid.
Well, I tried to,
Yeah.
it was disgusting.
I ended up having something wrong because I was using side units. I just
Yeah, cool, good. Don't do the area way. It's hard.
Where did that dy come from the closed integral x dy?
Okay. So this is me thinking Green's theorem really hard at this
I mean, I
thing.
got like where you got the x in this.
So Green's theorem is this, right? The integral of the partial of q with respect to x minus the partial of q with respect to y d area is the circulation integral around the bounding curve of p dx plus q dy. Right, and I said, okay, in my situation,
Okay.
I need 1 to be the partial of q with respect to x minus the partial of p with respect to y. I picked some vector field for which that would work. Like that happened to be the one that's 0, x. And then I put those in there.
Yeah.
And of course this piece zeroes out on you.
You did it like literally before we were assigned this take-home quiz. You gave us an example of how to do that.
Yeah.
So
This is a useful trick to know because it lets you switch from area integrals to kind of an easy circulation integral. Sometimes you can get away with changing horrible bounds into easy bounds by using this. Like this is a nice example where horrible bounds turn into easy bounds. You guys go with that? Okay.